We now have our update equations, and it's time to finally discuss some implementation details for a two-dimensional finite difference time domain code. First, we'll review what we've done the last couple lectures involving the PMLs and our update equations. And then before we jump into this, I want to remind you again of the code development sequence. We would never just write our fully functional code and when we're done that, hit run for the very first time. So I want to remind you of that. Given that, before we jump to 2 dimensions, I want to touch on the boundary conditions for 3 dimensions. That's pretty simple, just a little bit of an extension of what we've already talked about in previous lectures. But that'll put a nice period at the end of that sentence for 3D. At that point, we'll be done with 3D for a while, and we will take our set of 3-dimensional update equations and reduce that down to 2 dimensions. And as we have seen, Maxwell's equations decouple into 2 distinct modes in that case, and so we can talk about an E mode and an H mode. We need to calculate the PML parameters, the sigma x, sigma y, on this 2-dimensional grid, so we'll talk about that, give you some example numbers, and then discuss the implementation for the EZ mode. So this is the order that things happen in. Remember, now that we have the PML, we have integrations and other things happening. And then we can talk about the total field scatter field source in a 2-dimensional setting. So we said we need a way to absorb outgoing waves, and this makes those waves appear as if they just go off to infinity. And we realize we really need something that is anisotropic at the edges so that we can incorporate loss while also keeping the impedance matched, and we can do this for all angles, all polarizations, all frequencies. And so we ended up with a uniaxial PML. We then incorporated the uniaxial PML into Maxwell's equations, and we were in the frequency domain at this point. That's step 1 on this slide. At this point, we needed to multiply everything out and rearrange terms so that we're either multiplying a term by j omega, dividing a term by j omega, or not doing anything with j omega with the terms. And then we can use this little chart in the upper right to help us convert from the frequency domain to the time domain. So every term multiplied by j omega becomes a time derivative. Every term divided by j omega becomes an integration in time, and the others nothing really happens to. And so we end up at step 3. We have now a time domain equation with a PML incorporated, and the PML is causing us to have to do integrations now. We then, through a rather long process, we converted this to numerical form. We approximated the derivatives with finite differences, and we approximated the integrals with summations. And there were some tricks in there. But we ended up with a big finite difference or a numerical equation. We then solved that for the field value at the future time step and ended up with a slightly more complicated update equation. It not only contains the field value at the previous time step and the curl, but 2 integration terms. We're integrating the curl and we're integrating the field at every iteration. And our update coefficients became very large and ugly. But that's what we did. And now we had the update equations for all of our field components. Some discussion about what has to happen first or second. We're updating those integration terms before the update equation, for example. But we have more to talk about. And that's the purpose of this lecture. Remember the code development sequence. The very first thing we'll do is not do anything with a perfectly matched layer, just our basic update equations. We'll put a simple soft source somewhere in the grid, not quite at the center, offset. That way this radiated ring hits one of the boundaries before the other. And if we use Dirichlet boundary conditions, we should see the wave reflect off of the boundary. If we use periodic boundary conditions, we should see it leave one side of the grid and come in at the other. So at this point, that soft source, it's not really a controllable source. All we're really using it for is to throw power at our boundaries and see what happens. And also make sure that the numbers aren't exploding as our algorithm is running. Then the big step that we've spent the last few lectures on, we add the PML. And while small in the picture, obviously that was a pretty large numerical step to do that. But if we do that, we should see this radiated ring hit the PML regions, not reflect off of them, just get absorbed. And to the inner part of the model, it looks like that ring just kind of goes off to infinity. What we'll start talking about today is at step 4. We will turn off the PML on the left and right sides, make it size 0. We'll retain the PML on the top and the bottom, and then we'll create a total field scatter field source that goes across our grid and launches essentially a plane wave pulse in the vertical direction. It's still a one-way source. We don't want backward propagation. With no backward propagation, that really makes it a lot easier to calculate reflected energy, and it also minimizes energy that hits the PML. Remember, that won't work perfectly, so the less power that hits it, the better it will behave. Then we'll add in calculating the response, transmission and reflection. So we'll move the total field scatter field source. We'll add in our integrations. There's a lot more integrations now because we need to integrate all the way across the grid, or Fourier transform all the way across the grid. And then we add a device and we start modeling a device. And we'll simulate and benchmark at each step here. It's really, really important to stick to this. Okay, so we have these curl operators in Maxwell's equations, and we isolated the curl calculations into these curl terms that we're calling C. Now we also know from a previous lecture that our boundary conditions are isolated to these curl calculations and not in the other sort of updates or integrations that we have to do. They're isolated to these curl calculations. And why is that? It's because the curl calculations are the only ones that contain x, y, z derivatives. Those are the ones that are reaching out into adjacent cells in the grid. And so it's here when we're at the edge of the grid that they may reach outside where we don't actually have any stored values, and we need to handle that. So the boundary conditions we've isolated to our curl computations. So how do we handle this? In 3 dimensions. Well, we really have already seen this when we talked about the 2-dimensional formulation without the PML. So, for example, here is the x component of the curl of E. And we actually have 4 conditions to handle. We have the main finite difference equation, which is throughout all of the grid except at the edges. At the y high side of the grid, we have an issue. Why? Because we need a field value from outside of the grid at j plus 1. Well, we don't have that. So for periodic boundaries, evidently, what we're doing here is we're reaching to the other side of the grid and we put in a 1 for j. If we were doing Dirichlet, we would have a 0 here for the entire term. Another place we have a problem is at the z high side of the grid. That's because we have a k plus 1, and that would be outside of the grid. So what do? We put a 1 in place of that k plus 1 term. We're reaching to the other side of the grid. This is periodic boundaries. We would just put a 0 in here for Dirichlet boundaries. And then a 4th when both of these are the case. We're at both the y high and the z high side of the grid. And both the k plus 1 and j plus 1 would be reaching to the outside of the grid. So we simply put in periodic boundaries for both of those. And if we want a Dirichlet, we would put in 0s for both of those. So that's how we write our curl computation with the boundary conditions. And we want to implement this in MATLAB without using if statements. So here's how I like to do it. Just slightly different than what we talked about before, simply because we're in 3 dimensions now. Because we're in 3 dimensions, we have 3 loops. We have to loop over x, y, and z. And so what I do is I just write these loops over the entire grid, and I put in the sort of the MATLAB equation for our curl calculation. Then I'll notice, well, I've got these 2 terms. Those are our 2 problem terms. We're going to have troubles at the y high and the z high side. So what I'll do, noticing first we'll have problems at the z high side, I'll take the loop and not go to big NZ, I'll go to big NZ minus 1. That way there won't be any problems with the term in here, at least in terms of the z high thing. I'll copy and paste this line of code, paste it down here, and for periodic boundaries, I'll stick a 1 in here. If I was doing Dirichlet, I would put a 0 here. Now, we still have a problem at the y high side. So we'll take the y loop. We won't go to the end. We'll go to just y minus 1. So now everything inside that loop will not have a problem. However, we still have to handle the little ny equals big ny case. So we copy everything inside that y loop and paste it down here and handle it explicitly. And so we have a 1 in this place and a 1 in this place. And if we want a Dirichlet boundary conditions, this is periodic. If we want a Dirichlet, we'd put a 0 here and a 0 here. And so that's it. That is our complete curl computation. That is just the x component of the curl of the electric field. We would have a similar group for the y component and the z component in 3 dimensions. Now we want to take our 3-dimensional update equations and reduce them down to 2 dimensions. So let's review again what it's meant by a 2-dimensional simulation. Everything in the world is 3 dimensions. Even if we're running a 2-dimensional algorithm, we are modeling a 3-dimensional device somehow. So let's understand what that means. Here we have a ruled grating that is of infinite extent in this z direction. It's also of infinite extent in this x direction. It's just periodic and repeats. And then in the y direction, it's not of infinite extent. So we'll wrap a little window around 1 unit cell, and this would be our 2-dimensional representation of this object. We put a periodic boundary condition on the left and right. That makes this look infinitely periodic left and right. We'll have our absorbing PML boundary condition at the top and the bottom to absorb outgoing waves. So you can imagine taking a total field scatter field source, a one-way wave, and launching it into this device and watching it bend and wrap and resonate and do other things. And so we would populate our 2D grid in terms of the permittivity, putting 1s up here for air, 3s down here for the teeth, and then 2s down here for the substrate. Now, even though this would be a 2-dimensional simulation, we really are simulating a 3-dimensional object. In and out of the screen here is our 3rd direction. And when we're modeling a 2-dimensional thing, that 3rd dimension coming out of the screen, that's of infinite extent. So we're extruding this device out to infinity. So we really are modeling a 3-dimensional device. And the last thing I'll mention is never ever feel bad taking a full 3-dimensional device and reducing it down to a 2-dimensional simulation. That is very good practice. Don't feel like you're cheating or anything like that. If there's ever a time where you can reduce the dimensionality of your model, it is always good practice to do that. So here's another picture. If first we're handed our 2-dimensional grid and we see a little circle here, very often in the literature they'll call that a cylinder. Well, why on earth is that a cylinder if we just have a 2-dimensional simulation? Remember that 3rd dimension, so it's in and out of the screen here, really is infinitely extruded. So this kind of array is really what we would be modeling with this little unit cell in memory, a periodic array of cylinders. That 3rd dimension is infinitely extruded. Okay, enough of that. So that 3rd dimension, the z direction we'll choose it to be, is infinitely extruded. Further, we will restrict propagation to be in the xy plane. So that means there's absolutely nothing that can change in the z direction. If nothing changes in the z direction, then any derivative we take in the z direction has to be 0. So that's exactly what we do. And if nothing interesting is happening in the z direction, we don't need the z-axis PMLs. So right away our sigma z is 0 and our s sub z is 1. We can take those simplifications and plug those into our update equations, and they reduce down considerably. So here's how we would revise the update equation for hx. Anywhere I see a sigma sub z, so for example here, and here, and here, and here, and here, those are zeros. So if we set those to zeros, a lot of stuff cancels. We also see that this entire update coefficient cancels. That means we don't need this integration term where we're integrating the magnetic field. We still need the integration for the curl evidently, but we don't need this one. So it's a whole update coefficient that we no longer have to calculate. So that's how we do our revisions. Oh, and also the The z derivative in the curl we no longer need. Since this updated coefficient 0, we also don't do the integration. So a lot has simplified here. So here's our revised update equation for h sub x after we've canceled everything. So things are a little bit simpler here. The update coefficients are a little bit simpler. We only have one integration. The curl calculation is a little bit simpler, and we only have 3 terms in our update equation. But it's pretty simple to go from the 3D update equations, just cross off everything you don't need, and reduce down to the equations for 2 dimensions. Similarly, here's the update equations for h sub y for 2 dimensions. The same for h sub z. The same for d sub x, d sub y, d sub z, and the electric field components, the E fields. There's actually no changes there. Okay, so now we have our revised update equations. Now we have to think more about the PML parameters. So here's the MATLAB code to calculate these PML parameters. Essentially, we're going to have 2 2D arrays, one for sigma x, one for sigma y. So we need to populate a grid with this equation and also this equation. And so here's the MATLAB code for doing that. The trick here is we will eventually need to assign a sigma x and a sigma y to our different field terms. So we have this whole Y-grid staggered problem to sort out. So what I like to do is calculate these sigma terms on the 2x grid. So we're not really building a device here. In a way we are. We're building our PML. So we're employing this 2x grid concept. So I calculate sigma x, sigma y on a 2x grid and then parse it down however we need it. So once we do this, we'll have 2 terms and we could visualize them and they would look something like this. What I did as an example is I grabbed a slice through sigma y, just one vertical slice, and I looked at the numbers for sigma y. And what you can see in the middle section, it's all zeros. This is the problem space where the device would be and the actual modeling is happening. And then we see the numbers here go from 0 and increase up to about 0.03. And we see the exact same numbers down here. I'm using the same size PML on the top and the bottom. And the numbers would look the same for sigma x. It's just they would be running horizontally instead of vertically. And by the way, these numbers come from this case where I have a certain value for my free space permittivity and I have this value for the time step. So this should just give you an idea of what they look like and what types of numbers you should be calculating. Now that we have the sigma terms, the next step is calculating the update coefficients. So on the right, I'm showing the analytical equations for the update coefficients, and on the left is the corresponding MATLAB code that calculates these. Remember, sig x and sig y are on the 2x grid. These update coefficients are on our Y grid or the 1x grid. So we need to sort of parse down the 2x grid parameters to the 1x grid. This first set of equations is in the update equation for h sub x. So we need to pull off where sig x and sig y exist at the points where h sub x exists. So that's these 2 sigma parameters, and that's what we use in these update coefficients. In the second set of code, this is associated with the update equation for h sub y. So we need to pull off sig x and sig y at the points where h sub y exists. So here's the 2 sigma terms on the 1x grid where h sub y exists, and those are what we use to calculate the update coefficients. In this third set, this is associated with the update equation for the dz component. So we go to sig x and sig y and we pull off the points that are at the same points as d sub z. And we have our 2 sigma terms that then we use in our update coefficients. Let's talk a little bit more about implementation of the EZ mode. So here's how we'll initialize now. First, up front in our dashboard, if you will, we're going to define all of the device parameters. How big is our device? What material properties is it made of? What do we want to learn about it? What frequencies do we want to calculate reflectance and transmittance? Then we'll define our FDTD parameters. What type of grid resolution do we want? What type of time resolution do we want? Given that dashboard, we're done. Now we'll start calculating things. We'll calculate our grid parameters. This is grid resolution. We snap the grid to critical dimensions. We calculate how many points on the grid we have. Then we'll build our device on the grid. Then we can calculate our time step. Then we calculate our source, probably a Gaussian source. Now we're ready to calculate all of the PML parameters, the sig x, sig y. Given those, we can calculate all of our update coefficients. Then we initialize all the fields to 0. Now for the EZ mode, we only have HX, HY, DZ, and EZ. So 4 arrays will set all to zeros. We also have curl calculations and integration calculations. We set all those to 0 as well. Now we're ready to enter the main loop of finite difference time domain. So here we go. We iterate over some number of steps. The first thing we'll do is calculate the curl of the electric field. Given that, we can update the integrations where we're integrating the curl terms. Given these integrations, we can update the H field. Given the H field, we're done doing that. Then we can calculate the curl of the H field. Then update integrations for the D field update. Then we update the D field. Then for a simple soft source, we can inject that here. We're just showing overwriting one point here to put a little dipole radiating source, this little cylindrical wave that we see radiating outward. Once we know D, we calculate E from D, and we're done the updates. We probably want to visualize the fields and then keep repeating this process. A few things to remember when we're calculating the curl. This is a double loop. We're looping over X and Y and calculating these. These two parameters are 2D arrays over the entire grid. We also update our integrations everywhere there are integrations. We know already there's only integrations inside the PML region. It may be easiest just to store integrations over the whole grid, and our update coefficients will just be 0 outside of the PML, so everything will work. It's a little bit slower than it would have to be. A little bit fancier way would be to only store these integration terms in the PML regions. We probably won't do that here, but keep that in mind. Would be a big boost in efficiency. Updating the H field, again, that's a loop. So we have a lot of double loops. We're double looping over X and Y, double looping over X and Y, double looping over X and Y. In almost all of these, we're double looping over X and Y, except where we inject the source and also visualizing the fields. So we have a lot of loops going on. And this is actually one drawback of MATLAB. There's a lot of manual work happening here. And a compiled code would actually be considerably faster than MATLAB running this. But considering what MATLAB is doing, it's still amazingly quick. And for anything we're doing in this class, it's not going to hold us back at all. We can do a similar thing for the HZ mode if we wanted to simulate that. But it follows the same block diagram. The only difference is we have different update coefficients to calculate. We have different fields and integration terms to initialize to 0, and that makes sense. And the block diagram is still about the same. We'll calculate the curl of E, update the H field integrations, update the H field, inject an H field source, calculate the curl of H, update the D integrations, update the D field, update the D field, and maybe visualize the fields, and just keep iterating this until the end of the model. And the last topic here is our total field scattered field plane wave source. And you'll notice this is just a little bit of an extension of what we did for the one-dimensional model. So we'll define what the total field scatter field is again. We divide our grid, we're showing a two-dimensional grid here, up into two regions. So this dashed line is the boundary between the two regions. Below that, we'll call the total field region. And that contains both the source and the field scattered from our object. In the scattered field region, we don't see the source, but we do see the waves scattered by the object. A simple way to think about this is a one-way source. We launch a one-way source from this way down. Think of a laser pointer. It just shines in one direction. Doesn't really shine any light backwards. So up here is the scattered field region, and down here is the total field region. Some benefits of this: if we did launch a source backwards, that would hit our PML. PMLs don't work perfectly, and that would reflect a little bit, and that would hurt our model and accuracy a little bit. So we're minimizing how much power hits the PMLs. Also, at the boundaries, if we're looking at the field here, we are guaranteed that as a wave moving completely outward. That really simplifies things for calculating reflectance. And it lets us control the amplitude of the source really well. So here's how we will lay out our grid and the strategy. We have a device that we want to model. We put this in the middle of our grid. At this point, we need the spacer region between our device and our PML, and that needs to be about 1 wavelength large. Now, if we're calculating a range of frequencies or a range of wavelengths, we'll go with the lowest frequency or the longest wavelength, and we'll make that spacer region that. And we do that on the top and the bottom. We need the space between the device and the PML. And this is something we'll talk about in a following lecture, but very often we can get evanescent fields or temporarily guided modes in our devices that have these evanescent fields that come off. If those touch the PML, that's bad. That's bad because we won't be counting the evanescent fields as transmitted or reflected. However, the PMLs will couple to them, convert those into propagating waves in the PML, and essentially suck power out of your model. And that'll make sense later. Our PMLs will usually make about 20 cells on the top and the bottom. We'll model a lot of periodic structures in this class, so we'll be using periodic boundaries on the left and the right instead of a PML, but that's not necessary. You have all the equations and hopefully the know-how now to put a PML all the way around. But that's our layout. That's how we'll do things. The last thing I'll mention is that the position of this source is rather arbitrary. I tend to like to put it right up against the PML, but if you want to visualize the scattered field, you might want to move it closer to the device. In principle, it can be right up against the device without problems. It cannot slice through the device. So it has to be above the device. And also where we put that interface, it has to be homogeneous. We will be injecting a plane wave source. Plane waves only exist inside homogeneous materials. So if we slice through our device and tried to inject a plane wave, we'd get a very crazy result from that. Anyway, this is our grid strategy and how we'll do things. If we wanted to model something that was not periodic and it's of finite size, scattering off of an airplane or something like that, we will put that object in the middle of the grid. We still follow the same rules. We still have this spacer region on the left and right, top and bottom, that's about a wavelength. We'll have our PML region, and still 20 cells usually works pretty well. I like to have about 2 cells between the PML and my total field scatter field interface. Notice the total field scatter field interface goes all the way around now. But we're following the same rules as before. Now, when we define total field scatter field, we need to know how to modify our equations. Well, the problem occurs and the solution occurs at the interface. In the scattered field region, we have finite difference equations that are reaching over to the total field side. Well, now we suddenly have a total field term sitting in a scattered field equation, all with every other term being a scattered field quantity. That's not compatible. We have to fix that. Likewise, our finite difference equations in the total field reach over to the scattered field, and suddenly we have a scattered field quantity sitting amongst a bunch of total field quantities. That's not compatible, and we have to fix it. When we fix our update equations on both sides of the interface, that is suddenly our one-way source. So the finite difference equations that reach across the interface occurs in these curl calculations. That's where we have our spatial derivatives in x and y. So let's say at the y-index, j source, that's where we'll be injecting our source, our one-way source. So in our curl computation up here in the scattered field at j source minus 1, we have this expression. What I'm highlighting in red here is a term from the total field side sitting really in a scattered field equation that will eventually get incorporated into a scattered field update equation. But this in red is a total field quantity. How do we make a total field quantity look like a scattered field? We subtract the source from it. Well, now we can take this little source term, pull it to the outside, and we end up with this expression. What's neat is if we look at this expression, that is the original curl calculation. This means we can calculate the curl across the entire grid without thinking anything about the total field scatter field. And then just at all of these points across the grid, we simply subtract this little correction term to incorporate the source. But we'll incorporate this at every point that's on the interface of the total field scatter field. So we'll go all the way across the grid. So in fact, this term will sit inside a loop that loops horizontally across the grid in the x direction. Now we're on the total field side of the interface, and we have a curl computation that's on the total field side. However, it contains a term from the scattered field side of the interface. This scattered field quantity is sitting a whole bunch of total field quantities. How do we get a scattered field quantity to look like a total field? We add the source to it. Then we take the source term, pull it to the outside, and we arrive at this final expression, and the same interesting and useful thing happens. We get our original curl calculation back. This means we can loop over the entire grid and calculate our curl as if we don't know anything about a source. And then when we're done that, in a separate loop, we will set up a loop that goes horizontally across the grid just one time, and in all of these curl computations, all the curl terms in this row, we just simply subtract this little correction term. And that's it. But we still need expressions for our E field source, which is on the total field side, and the H field source on the scattered field side. So not only are these sources offset in time, they're offset by a half cell in space as well, and potentially different amplitudes, because one is E and one is H, and they're related through the impedance of the material that overlaps where we're injecting the source. So we really already have done this, and we will let this E field source be our Gaussian, so it'll be unit amplitude Gaussian, and we'll also eventually delay it by 6 taus and stuff like that. All those equations still apply. The magnetic field for the EZ mode has a negative sign here. The amplitude's a little bit different according to the impedance of the material. We have another Gaussian. However, there's a delay through half of a cell, and there's also a delay for half of a time step. So those are the equations we'll use to calculate the E and H source. And we really have already done this in the one-dimensional finite difference time domain code. So how do we modify our block diagram? Well, it's the same block diagram here, except after we calculate the curl of E, we will loop across the grid in the x direction and put those terms in that do our total field scatter field source, the correction terms. Then we update the H integrations, update the H field. Then we'll calculate the curl of H. Once we're done that, we loop across the grid and inject those little correction terms into that curl of H. That's the total field scatter field source, and the combination of these two is what launches our one-way source. Then, as usual, we update the D integrations, update the D field, update the E field, and maybe visualize our fields. And we march this over time. For the HZ mode, it looks almost exactly the same. And these updates or the corrections for the total field scatter field come after the curl calculations. So we'll calculate the curl of E, then we'll loop across the grid, not the whole grid, just in the x direction to incorporate those correction terms, update the H integrations, update the H field, calculate the curl of H. After we're done calculating the curl of H, we loop horizontally across the grid and add those correction terms, then update the D integrations, update the D field, update the E field, visualize, and just keep repeating this and marching over time. So all we did was add a step after each of the curl computations to incorporate these correction terms.